weather and weather forecast for my job, but the approach is slightly different. What I will try to bring you here is an understanding of how, the very basics of how the weather works. And from there, we will make a short trip to some basic forecasts, in a way so that you can start learning how to use weather information in order to make some decisions and to plan your trips. I would also like to say that if at any moment you can't hear me well, either because there's a problem with the microphone or something, just let me know. Don't let me talking here by myself if you can't hear me. So I will share my screen with you now. So can you see me? My screen, I mean? Ricardo, do you see my screen? You're muted. Okay, so there we go. So okay, here we go. So what is weather? The weather is basically how the gases in our atmosphere work. And the weather changes, weather systems exist whenever you have some kind of atmosphere, okay? It's not something unique to planet Earth. In fact, every planet which has some sort of atmosphere, even if very thin, it will have a lot of weather systems like clouds, tornadoes, storms, etc. I gave you here a few examples, like we have Neptune, you can see a lot of clouds. You can also see here, it's planet Earth, there's a hurricane here, it's a satellite image. We have some pictures, a picture here of Jupiter, and Jupiter has huge storms, some of the storms are bigger than planet Earth and has winds that reach thousands of kilometers per hour. And the last one, bottom right, is a picture of Mars. And actually, it's very interesting because Mars has a very thin atmosphere, which is 1% of Earth's atmosphere density. And still, it has some events like, in this case, you can see here, a small tornado. So what creates all these dynamics? What leads to gases, mixture of liquids and gases to move around and annoy us when we go to work or push a sailboat to move? Basically, in the very beginning, and the most important thing, it's the sun. Okay, the sun gives us radiation, gives energy, which gives increases temperature of gases in the atmosphere, of the ocean, etc. And then we have also a very interesting thing, which is, because if it was, you had just the sun and the planet and nothing else, temperature would be distributed according to the surface exposed to the sun. And so here's the first thing. You have part of our planet more exposed to the sun than other parts. As you move away from the equator, you get less sunlight and you have a lot more radiation being filtered by the atmosphere because the sun rays will hit the atmosphere in a certain angle, which will leave the perceived, so to say, thickness of the atmosphere to be higher, which will filter a lot more sun rays. So there's the first thing. Not everybody's getting the same amount of sunlight. The second thing is that the planet is twisted, and this angle changes along the years, along thousands of years. Right now, it's roughly in 23 degrees and a half, which means that as the sun goes around, as the Earth goes around the sun, the hemisphere, northern hemisphere, gets less sunlight in our northern winter, and the southern hemisphere will get more sunlight. And as it goes around, this changes. And there are two moments during the year in which the sun hits the equator and changes. You have this change in which you start to get more sunlight in one of the hemispheres than compared to the other. These are called the equinox. So you can see here schematics. This is pretty much obvious, but it's the most important, one of the most important things to understand why the weather changes so much. Why is it so dynamic and never constant? Another thing which is important, I mean, you can say, okay, so we get this angle, etc. But why is it that, for example, the weather in Lisbon is so different from the weather in Madrid? They're pretty much close. They're more or less in the same latitude. Or if you compare to some American city in the US, Eastern Coast, you can have huge differences. You can have 40 degrees in the summer for long periods in Madrid, whilst usually in Lisbon, it won't be more than 30 something, sometimes can reach 40, but just for a few days. And in winter in Madrid, you'll get negative temperatures, whilst this doesn't really happen in Lisbon. If you go to American Eastern Coast, you'll get snow, sometimes at the same latitude. So the thing is that the planet is not uniform. We have big masses of land, then we have oceans, and everything is pretty much scattered in a very random way. So oceans and land play a huge role in how the atmosphere behaves, because land, especially water, carry a lot of energy, and the currents in the ocean carry a lot of heat. So you see, all these things added up make the weather forecast quite difficult. Our atmosphere is a mixture, basically and mostly, of nitrogen, 78% roughly, and 21% of oxygen. Then we have 1% of other gases like carbon dioxide, carbon monoxide, argon, helium, hydrogen, etc. And the atmosphere is divided because we decided to classify it in different layers. The most important one for us for weather analysis is the troposphere, which is the first layer closer to the ground. And temperature, standard temperature, like average standard temperature, is considered to be 15 degrees. It's like an average, and it's an ideal atmosphere, okay? As you go up, you can see here on this graph, on the left one, shows how the temperature changes as you rise up in the atmosphere. And it starts to diminish until a certain point, it stops diminishing, remains slightly constant, it increases a little bit until it reaches stratopause, then decreases, then increases back again. So this first layer is the most important one, and remember this tropopause. It will be important for later. And just as a curiosity, the reason why temperature at some point increases a lot is because of radiation absorption by ozone, which exists in the higher atmosphere. We also see on the middle graphic that the pressure, atmospheric pressure, diminishes as you go higher and higher. And there's one important thing, scientists started to analyze the atmosphere and its behavior, and they, apart from realizing that the temperature diminishes as you go higher, what also happens is that when the air is heated up by the sun, it starts to elevate because it expands, so it becomes lighter. And there's an interesting concept, which is the gradient of air, dry air, or air with moisture, and the way it changes the temperature as it goes up due to the expansion. Let's imagine, it seems a bit complex, but it's actually quite simple. Let's imagine this air bubble here in the middle, and it's heated up by the sun. It starts to expand, it starts to elevate. As it starts to expand, its temperature starts to diminish. If you compress a gas, it will heat up. If you expand, the temperature will cool down. There will be less collisions of the molecules. So there is more or less standard rate by which this air will diminish by the expansion. And if the air is dry, it's roughly 10 degrees Celsius. In fact, it's 9.5, but let's round it up to 10 degrees. If the air has a lot of moisture, then the rate would be around 6 degrees Celsius per kilometer. So you have an interesting thing here with it, which is this will define whether the atmosphere is stable or not. So if the rate, the temperature of the air is diminishing on that day, diminishing faster than the air bubble you have here, what happens is that the air bubble will have the tendency to always be warmer than the air surrounding it, which means that this air bubble will tend to go higher and higher because it's always warmer, it's always lighter. So we would say that the atmosphere is unstable. This is also an important concept to understand cloud formation, for example, which we will be talking about later. So regarding the atmosphere around the planet, if scientists decided to make some calculations and they realized that if planet Earth would get a lot of heat near the equator because it's more exposed to the sun, less heat in the southern pole and north pole, then you would have to get a lot of heat near the equator, and poles should be really, really cold, way colder than they are actually, and the equator should be way warmer. In fact, they are not that cold, and the poles are not that cold, and the equator is not that hot as expected, which means that this heat, this energy is somehow being distributed, pretty much like money. Not everybody gets the same amount, but in a way, part of it is being distributed, not equally, that's for sure. So there's this guy named Hadley. He theorized that the air is circulating around the Earth because as it's receiving radiation from the sun, it gets lighter. And at some point, the air near the surface is replaced by cooler air coming near the surface. And so you have this kind of cells which repeat around the globe, okay? And this line here, this red line you see here, is the troposphere, is where our first layer finishes. And this is the layer which is important to us, okay? The troposphere and the tropopause is the line. If you see this 3D map, it's easier to understand. It also shows us something important. The thickness of the atmosphere is not the same, is not uniform around the globe. It's way thicker near the equator and thinner near the poles. Near the poles is around average 8 kilometers, the troposphere, and near the equator can be as thick as 15, 16, 18 kilometers. We're talking about just the troposphere. So we have a very interesting and basic concept, which is, warm air tends to rise. If it, as it rises, cools down slower than the surrounding air, and the cold air will tend to come down. As it comes down and accumulates over the surface, you start to have high pressure. As the warm air goes up, it starts to create a low pressure. Basically, the pressure here is low because you're losing air, so to say. So basically, you have, the wind is created by difference in temperatures in different places, and will have the tendency to move, this very basic concept will tend to move from high pressure areas to low pressure areas. In fact, what happens is that, planet Earth is moving, it's rotating over itself. And this creates a very interesting thing, which is when something moves over planet Earth, it will carry the amount of movement being brought to it by the movement of planet Earth. Let's imagine that Peter Schrumpf is here near Uruguay, and João Bandeira is standing here in north of Brazil near the equator. And Peter will throw a tennis ball to to João Bandeira, I'm sorry. You know, the linear velocity of João Bandeira, who is here in North Brazil, is higher because although the angular velocity is the same anywhere around the globe, the linear velocity is not. You know, if you have a wheel, the edge of the wheel is moving faster than the center of the wheel. So what happens that when Peter throws tennis ball, the tennis ball will have the velocity which was given to it by Peter's arm, but also the velocity